the context of this is formal verification. That is, trying to make sure that our programs do what we want to do them. So how do we actually know that a program is correct for some definition of correct? And I suspect for most of us, the answer is something like this. We can just use testing. So at the left-hand extreme of this spectrum, you can write some tests which feed some defined inputs into your program and then check the outputs and see whether those outputs are what you expected. This is all very familiar. The problem with it being only that your tests are limited to whatever example inputs you dreamed up. And so if the bug only manifests itself with some inputs that you didn't think of, then of course your tests won't catch it. Now, in order to try and broaden that, people developed, for example, property-based testing, where we generate a whole bunch of inputs randomly and try to find ones which will cause some kind of condition to fail, which is good, but it's still like you're just exploring a certain limited state space here. Going even further along this axis, model checking tries to formalize things a little bit more, and in model checking we try to systematically go through all the possible combinations of what could happen, especially if different things could happen in different orders, for example. We will try to systematically try all the possible orderings in which messages could be delivered, for example. And this is already pretty good. It gives us some good assurance about the correctness of something, but with model checking, we're still limited to a finite search space. And the problem with the search space is that it grows exponentially. So if you have a protocol that can send a maximum of 5 messages, or you limit your search space to a maximum of 5 messages, then that's great. We can completely explore that. But maybe expanding it to 6 messages would now mean that your model check takes some multiple of the time to run. And so at some point, it just becomes unfeasible. So you have to bound the size of the model. And if you have a bug that only occurs in some execution in which 6 messages are sent and you bounded your model search to 5 messages, you won't find it. So the nice thing about proof is that with proof, we can use techniques like proof by induction, and we can actually prove things about infinite state spaces. So especially in a distributed system where any number of messages might be sent back and forth over the course of an execution, we can still prove that regardless of how many messages are sent, regardless how long this execution is, we can still end up in a valid state under all possible circumstances. And so this is what we want to do in this talk. Now, I won't hide the fact that doing proofs is a lot of work. And so you might wonder, is it worth the faff at all? Is it worth the bother? And there are a few reasons why you might bother. So for very run-of-the-mill code, it's probably not worth bothering trying to prove anything. So it's only really worthwhile in algorithms where we need some formalization, otherwise we just don't believe that they're correct. So there are plenty of algorithms which are subtle, especially when it comes to like concurrency or partial failures or things like that. And just by staring at the code, you don't necessarily convince yourself that it's correct. So because there's so many potential orderings of things that could happen. And these are then environments in which proof is extremely helpful. So if there's some kind of complicated state space that the system might go through, and in that case, actually doing a proof is useful not just for having the proof at the end, but it's actually just the process of writing the proof is itself helpful for us as humans to get a better understanding of what the system and the algorithm is doing. But there's one more reason for doing proofs, and this is thanks to my collaborator, Dominic, who came up with this wonderful quote that Isabelle is the tool we'll be talking about today, is the world's most complicated video game. And it does have something of that sort of fun, sort of puzzle game sort of nature about it, where you're thinking like, oh, maybe I can combine this fact with this other thing and this hypothesis here to derive this other thing, which I can then combine with the lemma over there, and then you're kind of placing these things together, and then at the end it works, maybe, and if it passes the check, and it's incredibly satisfying, so you've then like beaten the game at that point. So I want to, in this talk, actually convey a bit of the fun of that sort of interaction as well, so to give you a bit of a taste for what it actually feels like to do these interactive proofs. So I'm going to use a distributed system as an example and show how we can model a simple distributed system in Isabelle. Isabelle itself doesn't have any built-in support for distribution, any distributed models or so, but we can build one fairly easily. And so I did, for the purpose of this talk, I wrote a simple model of a distributed system in like 30 lines of code or something like that. And that's actually sufficient. And what we're going to do is to analyze a particular algorithm. I've chosen a simple consensus algorithm for today. So you might know consensus algorithms like Paxos and Raft. They are quite subtle and quite complicated and great examples for wanting formal verification because people find them hard to understand just informally. Unfortunately, we don't have time really to do a whole Paxos in this talk, so I'm going to do a very simplified consensus algorithm. It's still a consensus algorithm. It's just, it's not very fault tolerant, but it does work correctly. And so for a consensus algorithm to work correctly, we have to define what it means to be correct, and there are several properties that we expect of such an algorithm. The most important one is the agreement property, and that is that you've got several processes or nodes in a distributed system, and they might decide a value or learn a decided value. And whenever any two processes have learned some value, you expect those processes to have learned the same value. So this is like the fundamental agreement that you want in a consensus algorithm. If stuff gets decided, then everyone decides the same value. And so the simple protocol I'm going to be using works like this. So here we've got time going from left to right. We've got two users, the red user at the top and the blue user at the bottom. And the standard example of consensus is trying to figure out where to go for lunch, of course. That is one of the most important problems facing humanity. And so we somehow want consensus across these lunch goers, and the way we're going to achieve this in our very simple consensus algorithm is we're going to have a single node called the acceptor, which makes the decision. And so think of this like a leader in database replication, for example, or master. So it's just like a single dedicated node that is in charge of making the decision. And so what happens in this protocol now is that any proposer that wants to propose a value will send that value as a message over the network to the acceptor, and there's only one acceptor, and that acceptor is going to pick whatever value it sees first. So whatever value, whatever proposed message is the first to arrive at the acceptor, that is going to be the decision, and everyone else has to follow that one decision. And so in this example here, the red user wants to eat tacos, the blue user wants to eat falafel. The proposal for falafel reaches the acceptor first. And so the acceptor is going to, at that point, decide the value falafel and send a message back to the blue user saying, your proposal of falafel was accepted. Then the red user's proposal of tacos arrives second, and so by that point, falafel has already been decided, and so the acceptor is going to reply back to the proposer saying, sorry, I already accepted falafel. And so at this point now, both proposers, they learned the decided value, and they have indeed learned the same value, which is exactly what we wanted of this algorithm. So as you can see with this case, if our acceptor is offline or crashes or so, then the algorithm will make no progress, because we don't have any provision here for failing over to a different node or anything like this. So this is what I mean. It's a very simple algorithm, but it's enough to demonstrate proof in interesting ways. Okay, so this is sort of the execution of the algorithm. We can now abstract this a little bit. And the way we're going to model this in Isabelle is to break the execution into time steps. And so we can say that the system as a whole goes through a sequence of time steps, and in each time step, one of the processes is going to do something. And so, for example, here in the first time step, the red user requests a value at proposer 1. Time step 2, a user requests a value at proposer 2. In the third time step, a message is received by the acceptor. In time step 4, another message is received by the acceptor, and so on. And so we don't make any assumptions about the order in which the nodes or the processes here execute, so they can be interleaved in any arbitrary order. In particular, if a node sends a message, it might be delivered in any subsequent time step. So it might be delivered in the next time step, or it might be delivered 10 million time steps later. Both are equally fine, and from the point of view of the proof, we don't care about how long the network delay is, for example. We don't even assume anything about messages ever arriving. So it could be that a message is sent but never arrives, or it could be that it arrives 1,000 times. All of those things are possible. So we want to make very little assumptions here about the network, certainly no reliability assumptions whatsoever. And so we can break this execution into the sequence of time steps, which is actually very similar to how other formal modeling tools, for model distributed systems, so TLA+, which is a model checking tool you might have heard of, also has this notion of time built into it, actually, and it also has the linear sequence of time steps. In each of the time steps, I'm going to say that what happens in the time step is that one of the processes handles an event. An event might be a user requesting a value, it might be a message being received off the network, or it might be something like a timeout. And so we can now define our algorithm in terms of a step function. And so a step function has this type signature that you can see here at the bottom. It's a function that takes 3 arguments, and it returns a pair of 2 values. So the 3 arguments that it takes are, firstly, what is the identity of the process that is executing? So each process has some unique number or name or something like that. Secondly, what is the current state of that process? So each process has some local state that it can remember. There's no shared state across processes, only local state at each individual process. And thirdly, what is the event that has happened here? So is it a message received, for example, or is it a user request? So those are the 3 inputs. The outputs of the step function are, firstly, the new local state. So we pass in the current local state, and we get back an updated local state. And secondly, a set of messages to send. And so this can be no messages sent, or 1 message sent, or any number of messages sent at the same time. And so this is actually now enough to model the consensus algorithm. So I will just introduce a little bit more of notation so that you can just follow the Isabelle syntax. So this is just in comparison to Python as an arbitrary thing, because probably most of you have seen Python before. So if you want to write the identity function, that is the function that just takes an argument, returns that same argument, there are different ways you could write that in Isabelle. So there's the fun keyword and there's the definition keyword. They differ in subtle ways, but both are ways of defining a function, and the details, the difference doesn't really matter for the purpose of this talk. We also have anonymous functions. So in Python, you would write lambda x, colon x as the anonymous identity function. In Isabelle, you would just write a Greek letter lambda. And finally, then calling a function or applying a function to some arguments. In most programming languages, you'll have function name and then parentheses and the arguments in parentheses. Isabelle uses a more ML or OCaml style syntax, where we just have function name space, argument, and so on. So we don't need parentheses there. We have parentheses for grouping, but not for function application. OK, and that is actually enough, I think, to introduce our algorithm now. So what I want to do is to write the functions that will implement this particular protocol here, using the types that we had just now. So starting with this in pseudocode, we first of all have different code running on the proposer and the acceptors. So, there's a single acceptor, multiple proposers. They have different code running on them. That makes sense. So firstly, on the proposer, when the user makes a request, we want to send the proposal message to the acceptor, and then when the response comes back, the accept message comes back from the proposer, then we want to decide or learn the decided value, right? So that's what the proposer does. On the acceptor side, we just sit there waiting for proposal messages to come in from the proposers, and then depending on whether we've already decided a value or not, if we haven't decided a value, we decide a value and send it back. If we have already decided a value, we just send the previously decided value back. And so we can translate these functions into Isabelle now, and it looks something like this. So here, this is the Isabelle. It uses this kind of nice interactive IDE. Here I've just got at the top defining the the name of the file, essentially. Just a moment. Right, and so first of all, we define a data type for the messages that can be sent over the network. And so this is just a tagged union type like you get in many languages. So a message can be either a propose message containing a value or an accept message containing a value. Value here is just a type variable, so it could be anything. It's polymorphic. And now we have the function, the step function that runs at the proposer, and the step function that runs at the acceptor. So at the proposer, just looking back at the pseudocode, first of all, we have to handle the possibility that the event is a user request. And so the way this works here, this uses pattern matching, like you might know again from OCaml and many other languages. So here we have 2 arguments. The first argument is the current local state of this particular process. And I'm going to define here that the local state is an option type, or maybe type. And so this can be either none if no value has been decided, or some v if some value v has been decided. So the local state is just like a single optional value. And then the second argument is the event that occurred. And so we're saying here, if the proposer is in local state none, and it receives a request from a user, a request for value val, then what happens? So the return value is this pair, as I said. The return value, the first part, is the new updated local state. So here, previous local state is none, local state does not change, but we do send a message. So here the curly braces are a set of messages that we send. We send exactly one message here. The message we send is going to be a proposal message containing this value val, and this 0 here is the recipient of the message. And so I'm just going to define the convention that process number 0 is the acceptor, and processes 1, 2, 3, and so on are the proposers. And so we just give an integer number to each process and just designate 0 as being the special acceptor process. So this is the first part. I think this makes sense. Now, the second part is what happens when we receive the response. And so here the event that happens is that we receive a message. This underscore is who we received the message from. So the sender of the message, we don't care who sent the message. As we receive an accept message. And when we receive this accept message, now we update our local state. So our local state was previously none, and now we change our local state to be some val, where the val is whatever the value was in the accept message. And this is the empty set. That means we don't send any more messages. So that's the end. The final step here is just like the catch-all, and that is whatever otherwise happens, it just gets ignored. It's a no-op, because what happens here is whatever the state is and any event underscore here, the state remains the same, and we don't send any messages. So this is just the catch-all that means we match all of the possible patterns for the arguments here. Now the acceptor, let's looking back at our bit of pseudocode again here. So here we just have to handle the case where a proposal message is received from the proposer, and then depending on whether we've already decided a value, we do one thing or another. So here we're receiving a proposed message containing a value val from some process sender. And what we want to do is we want to reply back to that sender, and the reply here is going to be some accept message, but which accept value we send is going to depend on the local state. So the current local state here is some variable that we can pattern match on. If the local state is none, that means we've not decided anything yet. So in that case, we're going to update our local state to be some val, and we're going to send the accept message back. If we have already decided some value v, then our local state is going to remain the same. So we're not going to change the decided value, and we're going to send that value v back to the proposer. And again, we've got the same catch-all here at the end, where we just do nothing in all other circumstances. And so this is almost it. The only thing we finally need is a function that wraps up the acceptor and the proposer. So it's just going to take an additional argument, which is the process number. So if process number is 0, then we're going to execute the code for the acceptor, like I said earlier. And for all other numbers, we're going to execute the code for the proposer. So this is enough. This is the entire definition of the algorithm. So you can see like key features of Isabelle here. Well, actually, we're using the whole language here, which is like a functional programming language embedded in Isabelle. So it has static type checking, and it has type inference, like many functional programming languages. The only real difference is that this language is designed not so much to be executed, but more to be syntactically manipulated as part of the proofs. That's sort of a subtle distinction, which I don't really have a great amount of time to go into. So what I want to show instead is now how we can start proving things. And so in particular, we want to prove this agreement property for the consensus algorithm. And so I need to introduce just another bit of syntax and notation, maybe just as a reminder for people who haven't seen logic for a while. So this is just standard mathematical notation for logical implication. And this is, we're saying here, P1, P2, etc. are some set of assumptions. And if all of those assumptions are true, then we can conclude that the statement Q must also be true. So here the little hat is the AND operator. The rightward arrow is implication. So if everything on the left-hand side of the arrow is true, then the thing on the right-hand side must also be true. Sometimes this is written instead as sort of repeated arrow implications. These two things are exactly equivalent. They mean exactly the same thing. So okay, we want to formalize this agreement property. And so let's take this sort of human language English description of the property and formalize it a little bit more. So what we want to prove is this theorem now stated in a sort of semi-formal way. What we're going to say is assume that some variable state represents the states of all of the processes after we've executed some number of steps of the consensus algorithm. We don't care how many steps, so maybe 0 steps were executed, maybe 100 million steps, it doesn't matter. And the steps here is going to be a function from process ID, sorry, the states, the variable states is going to be a function from process ID to the local state of that particular process. So what this is saying here is if the state of process 1 is some value 1, and the state of process 2 is some value 2, for any processes, proc 1 and proc 2, what we must show is that in this case, value 1 must equal value 2. So this is just a rephrasing of the sort of English statement that we have above. And so now we can take this statement and write it in Isabelle. So the way we will do this is we will write a theorem. We can call this agreement. And first of all, I'm going to have the assumptions. So let's say, so the first assumption is here that we have some valid execution of our consensus algorithm. And so for that, I have defined a little helper function called execute. It's not very long. It's just like 20, 30 lines of code or so. If I have time, I can show it to you later. And we're going to say we're going to execute the protocol involving this function here, consensus step. So this is going to be our step function for the execution of the entire system. Now, the next argument I need to give is the initial state of all of the processes. And so I'm going to give this as a function from process ID to the initial state of that particular process. So I can just write this as a lambda function, a lambda that takes some process ID p, and it returns the initial state. And I'm going to just say the initial state of all of the processes is going to be none. So they start off in an undecided state. Okay, so this is just the option type. The next argument I need to give is the set of all processes that exist in the system. And so in some consensus algorithms, you might need a majority. In that case, you need to know what are actually the processes that exist. But for this particular consensus algorithm, it doesn't matter how many processes exist. So I can just give the universal set of all possible processes. So this can be an arbitrarily large or even infinite set of processes. So these are the three arguments I have to provide. So our step function, the initial state, and the set of processes. And what I get out is three variables, which I'm going to call events, messages, and states. And so what this is saying here is that the value of events can be now any sequence of events that occurred in the execution of this particular protocol. And messages is the set of all messages that were sent over the course of that execution. And states is the final local states of all of the processes. So states is going to be, again, a function from process ID to the local state of that process. So I can now use those variables. And so I can make more assumptions. So I can now say the state of process 0, that is, the state of process 1 for any process 1. Assume that the state of that process 1 is value 1. And likewise, assume that the state of process 2 is some value 2. And so this means that after some execution, these two processes have got into a decided state. And what I want is for them to have decided the same value, right? This is what we're trying to prove. So I can say here, what we want to prove is that value 1 equals value 2. And this is now an exact Isabelle formalization of this statement we had just here. Now, the next thing I'm just going to write here is sorry. So sorry is an Isabelle keyword that is absolutely wonderful. It just means, believe me, this is true. I'm not going to prove it. I'm just going to assert that it's true without proof. So, of course, I can do that for now. At the end, none of you are going to believe me if I have sorry on the screen. So our goal is going to be to get rid of the sorry. But sorry is extremely useful while you're developing a proof bit by bit, because you can't prove everything at the same time. You're going to have to start with a few things assumed, then see how far you can get using those assumptions, and then later prove whether your assumptions are actually true. And so I'm going to show you in a moment how we can actually do this kind of refinement here. So But first of all, this is the theorem that we've stated. The next step will be now to try and figure out how to prove it. Now, to prove it, a typical technique that is often used with consensus algorithms and these kind of things is to introduce invariants. And so an invariant is just some kind of statement that we believe to be true at every step of the execution, and where we can show that every step of the execution maintains the invariant. So if the invariant was true before and we execute one step, then the invariant is still true afterwards. And this is actually the most tricky part of the proof in some way, because nothing tells you what those invariants should be. So you as a human have to actually be creative and think of what a suitable invariant would be in order to prove this particular result. So this is the most creative part of the proof. Once we've got the right invariants, the rest of the proof is actually pretty mechanical. So I'm just going to introduce two invariants here, and then we can reason about those a little bit. So the first invariant I'm going to say is, assume any proposer P. If the state of that, the local state of that proposer P is some val, then there must exist some process A that has sent an accept message containing that value to P. Okay, so this is kind of saying there's a connection between the local state of a proposer and an incoming message. And so do we believe this? Well, okay, so the only way how a proposer can get into a decided state is here. So this is the only thing that changes the local state of a proposer, and it does so in response to an accept message. So this looks kind of plausible. So it's an accept message that triggers the fact that the proposer switches into this decided state. Okay. Second invariant we want now is if some message accept val has been sent anywhere in the system, then the acceptor must be in the state some val. Do we believe this one? Okay, well, how does an accept message get sent? Well, a proposer never sends an accept message, it only receives an accept message. So the only way how an accept message gets sent is on this line and this line. So these two lines in an acceptor. And we're going to see here that, well, if accept val gets sent, then the state of the acceptor is some val. And if accept v gets sent, then the state of acceptor is some v. Okay, so we seem to have this correspondence between the accept message and the local state of the acceptor. So this second invariant also looks plausible. So I think we've sort of informally convinced ourselves that these invariants hold. Now, we will still want to prove it later, but let's just take those as given for now. The next step is now to ask, if we have these two invariants, can we prove the agreement property from it? So in order to do that, in Isabelle, I will again introduce just a little bit more syntax. So this is just fairly standard mathematical notation. The upside down A means for all. So this means here for all possible values that the variable x might take, the statement P of x is true. And the counterpart to that is the exists quantifier. This is this inverted E, where we say there exists at least one value for the variable x such that the statement P of x is true. There might be multiple values, but there will be at least one value x for which this is true. And so these quantifiers are very useful for making the formal statements that we will need to do in a moment. So we want to now translate these two invariants here into Isabelle. And so what I'm going to do is to copy them from a different file to save a bit of typing time. So here we go. So we've got two invariants just as definitions here, and I'm just going to go through them again to make sure that everything is clear. So here, remember, the first invariant is for any proposer here. So we have here for all proposers and all possible values. If P is a proposer, so acceptor is process number 0, so proposer is any non-zero process ID. So hence here this assumption that process ID not equal to 0. This means it's a proposer. Now, if the state of P is some value, that is here, the state of proc is some value, then there exists some process, here the sender, such that this message was sent. So here in the set of messages that were sent, this thing here occurs. So we have this tuple here, which consists of firstly the sender of the message, then here proc is the recipient of the message, and this is the actual content of the message. And so here we are saying that if this is true here, this arrow here is the implication. So if the first line is true, then the second line must also be true. That is, there exists this message, so this accept message must exist somewhere in the set of sent messages. Okay? That's the translation of the first invariant. The second invariant, if a message except val has been sent, so here we have on the left-hand side of the implication, there exists some message here, this except val, and we're going to say this statement is going to be true for all possible senders, all possible recipients, and all possible values. If this message here exists in the set of messages, then the state of the acceptor must be some val. So the state of process 0, the acceptor, must be some val. Okay. These two invariants, this is the translation. Now what we want to do is to see if we assume these two invariants hold, can we prove the agreement property? So the way we can do this is we'll introduce a lemma. And so let's say that we just take this execution here, so with this definition of a valid execution, and we're going to just say that for any valid execution like this, the invariant 1 holds, and we have to pass invariant 1 two arguments, which is the set of messages and the list of states. So the set of messages and the list, the map of states, and invariant 2 also holds. And so I'm just going to say sorry on this. And so this is going to say, I'm just going to assume that the invariants hold. We can come back later and prove that they actually hold. But I want to now see if I can prove the agreement theorem under this assumption of the invariants. And so we said earlier, in formal reasoning, it's not immediately obvious that this is true. And so this is where Isabelle becomes really handy, because Isabelle can actually help us write the proof, not just check the proof, but it can actually help us write it. And so I'm going to go into proof mode here. And now I need to think how I would argue this logically. Like if I was going to write this proof on pen and paper, I would have like some intermediate steps. And so what I think I can prove here, first of all, like we've got the assumption that some process here has decided a value. That means there must be an accept message, and because we have the accept message, that must mean that the acceptor is in a decided state. So I think we should be able to show here from these assumptions that the state of process 0 is some value 1 on the basis of taking this value here, value 1 from the assumptions. And now I can invoke an amazing command, which is called sledgehammer. And sledgehammer is just going to try and find a proof automatically for this. And so I'm just going to leave it running for a few seconds and see if it can find the proof automatically.
10 minutes left.
Yeah, so normally it should be able to find a proof within a few seconds. So
It's been a few.
it's been a few seconds, yes. So, okay. Let me see here.
Well, you do have 10 minutes.
So I am then just going to copy a little bit from the other file because it's possible that I typoed it somewhere. So this is just the invariance lemma again. It should be, no, it timed out, so it hasn't found a proof, so I'm just going to borrow this one here. I think it's the same except for just using a prime on some of the variable names. Now it's found a proof. Okay, excellent. And here we go. And so I will explain this little cryptic line in a moment. And so what has happened here is that we've made a statement that we think we can prove automatically. So this statement should be simple enough that Isabelle should be able to figure it out automatically. And it has indeed been able to figure it out using a particular proof algorithm. So Metis is one of a whole bunch of different proof algorithms which are built into Isabelle. And what this command requires here, Metis does some kind of search on the rules that can be combined, blah, blah, blah. I don't know how it works internally exactly, not important. But we give it a list of facts that it can use. And so the facts we're going to give it are, first of all, the first two assumptions, that is these two lines here. Then we're going to give it the definitions of the two invariants, and we're going to give it the invariance lemma, that is this thing from up here. And so using all of those facts together, Isabelle, using the Metis proof method, has been able to prove that the acceptor is indeed in the state some value 1. Now, I should be able to do a very similar argument for value 2, shouldn't I? So let me just say that, moreover, I want to also prove that the state of the acceptor is some value 2. Sledgehammer. What does it not like? Missing the word have here. And it has found a proof, and the proof will look very similar to the last one, I suspect. Here we go. And so we again have Metis, and you notice the only difference between the two proofs is now we're using assumptions 1 and 3, whereas the previous ones used assumptions 1 and 2. So we're using this assumption here. So now we have that the acceptor is in state value 1, and we have the acceptor is in state value 2. So the only logical thing we can conclude from that is that value 2 and value 1 must be the same. So we should be able to show from this that value 1 equals value 2. Sledgehammer. And it's found a proof very quickly. This time it's using a different proof method. It's using simp, which means it's using like syntactic manipulation and simplification on the syntax of the expressions that are available here. And this completes the proof, so I can type QED, quod erat demonstrandum, and Isabelle down here tells us in our status that we have the agreement theorem proved, which is wonderful. Under this sorry, of course. So remember, we still got this sorry. This is what we're relying on. But we've made progress. So we have now shown that these two invariants are indeed strong enough, they are sufficient to prove that this agreement property holds. So the next step is then only to prove the invariance. But we've made progress, and this is really good news. And we haven't been able to make any errors in the reasoning. And so just to show you like that this is really true, so for example, let's say I delete the invariant 2 from this lemma here. So now we're only going to assume invariant 1. And now you can see that these two lines are highlighted in purple. And so purple means that Isabelle is sitting there spinning in the background trying to prove these, but it's just not managing to prove it. And it's because it's simply not true anymore, because now we don't have it. So this shows now that actually just invariant 1 by itself is not strong enough. We do, in fact, need both invariants. And so this is like part of this kind of fun game-like interaction that you can get with Isabelle. Like you can try and just change things a bit and see how it responds, and it gives you this immediate feedback here. So I'm just going to undo this, put invariant 2 back in. Now it's rechecking. So you saw for a brief moment it flashed up in purple while it was rechecking it, and then once it's gone white, then everything is fine. So how would we now go about proving that these invariants are true? So the next step is now that we think about the execution of our system, and as I said earlier, we want to show that if the invariants are true at one step of the execution, then they must also be true at the next step. And this way we can then build this up for arbitrarily long executions using a proof by induction. So what we're doing here is an induction over the list of events that occurred in the execution of this system. And so what you can think of this setup as follows. So all of the processes start off in some initial state, and then we have this list of events at the top, which are the events that occur in the system, and the current state and an event is always fed into the step function to produce the next state for that particular process. And then we can have arbitrary processes taking arbitrary steps, and what we want is that we can append one further event at the end of this list of events. And so now we're going to assume that our invariants are true in states, and we can prove that they are still true in states prime, so after the execution of that one step. And the way we can do this is induction. And so in particular, Isabelle supports induction on various things. You might know induction on natural numbers, where you show some statement is true for 0, and then you assume that some statement is true for n, show that it's still true for n plus 1, and then that shows that the statement is true for all natural numbers. This is great. Here we're doing induction on lists instead. So first of all, we have the base case, which is we proved that this some statement p is true for the empty list. And secondly, we're going to assume that the statement is true for some list xs, and prove that the statement still remains true when we append some element x to the end of the list xs. And so this is the inductive step. And if we have both of these, then we can deduce that the statement p is true for all possible lists xs. In this case, this means for all possible executions of our distributed algorithm in a distributed system, no matter how long those executions are. And so notice induction is something quite special, because what we need to do here is a finite amount of proof effort. So we just prove two things. We prove the base case, and we prove the inductive step. But from these two proofs that we've done, we can now make a statement about an infinite system, so an infinite set of lists we can prove the statement P for. So we only need to do a finite amount of work to get infinite bang for your buck, as it were. So this is very nice. And so I will show you very quickly in my last few remaining moments what this might look like. And so we can do a proof here. I'm going to try and prove this invariance lemma using the assumptions that we have. And I'm going to do a proof by induction. And I need to choose first of all, the variable that we do induction over, which is events, our list of events. That's what we're doing the induction over. Then I have to define arbitrary for the variables messages prime and states prime. What this means is that these variables are allowed to be different at each step of the induction. That's all what they mean. So they're not constant for the entire induction, but they're just local to each step of the induction. And now finally, I need to define which induction rule I'm using. And I'm going to use this induction rule on lists. And so this, I have to write this one line by myself. I have to decide myself what variable I want to do induction over, which induction rule I want to use. But once I have this, I can use Isabelle's code generation. And so you can see down here, I've already got a whole bunch of useful stuff. It says 2 subgoals. The 2 subgoals are indeed the base case and the inductive step of the induction. And I can just click this thing here down here, and it's going to give me the outline for a proof by induction. And so this outline consists of 2 cases. Nil is the base case for the empty list, and here snock is like appending one item to the end of a list. This is the inductive step, and each of these is filled with sorry for now, so this means I haven't done either of those 2 cases yet, but like my basic setup of the induction is fine. So now let's see if I can just do the base case. So maybe the base case is simple enough that Sledgehammer can even find it, and it can. Hooray, good. And so just give it a moment. And now I can click this again and put this in here. And so what we've done is proved the base case here. I can even copy this here to make it more explicit of exactly what it is we've proved. So what we've proved is that invariant 1 and invariant 2 hold on the execution that contains no events. So i.e., the invariants hold for the initial state of the system. And I've been able to prove this using fastforce. Fastforce is yet another different proof algorithm that's built into Isabelle. And fortunately, Sledgehammer has been able to find the lemmas and the definitions that I need to feed into fastforce in order to prove this. And this has now proved the base case of the induction. So if you see down here in the status, it's now saying 1 subgoal. Previously, it was 2 subgoals. So here, because the base case goal has gone away, only the inductive step remains to be proven. And so like this, I can gradually work my way more and more towards a complete proof of the whole thing. So I think I don't have time to run through the whole inductive step, unfortunately. It is another maybe 200 lines of proof code or so. But I will actually say those lines are much easier to write than what we've done so far. So once you know Isabelle, actually, the rest of the proof is pretty mechanical, because it's really just a big case split. Like, you consider all the possible cases of all the possible events on all the possible processes, just keep case splitting until it's simple enough that the automation can solve the individual cases. And so that will then allow us to actually prove that the inductive step, that is, that the invariants hold from one step of the execution to the next, and therefore that the invariants hold for all possible executions, which then gives us finally this agreement lemma, this agreement theorem, which is what we wanted. So I think I'll probably leave it there. I was thinking I might try and do like an online recording of this, where I spend 2 hours or so just going through the entire proof, because it is quite interesting to see. And this is a nice proof because it's manageable enough that you can actually take it in within a sort of semi-reasonable amount of time. It is a lot of work, but hopefully you've got at least a bit of the taste of this kind of fun, playful interaction that I like so much about Isabelle, this video game-like mode. If you want to see the full proof, I have put it here online at this URL. So that contains the full proof code and also the harness that sets up our little model of a distributed system. So it's a fairly manageable amount of code, and if you like, you can go there and take a look at it. So thank you all so much for coming.